Let's continue our discussion on radical expressions and functions. Here we have 3 functions and 3 graphs, and we need to determine the domain of the functions and then try to match them with their graphs. Granted, we could create a table of x and y values and figure out from those tables which graph corresponds to which function. But let's try using the domain. For our first function, f of x equals the square root of x minus 3. Remember in our previous lessons that we talked about how to find the domain of a radical function. We're going to take what's underneath the radical, and we want what's underneath the radical to be greater than or equal to 0. This will always be the case when we have an even root. Here, when there's no number, our index is 2, so this is a square root. Anytime we have an even root, we're going to set what's underneath that radical greater than or equal to 0 and solve for our variable. I do want to caution for a moment, a lot of times I see students forgetting to check the index. So please make sure you're checking the index to ensure that it's an even number before setting what's inside greater than or equal to 0. Why is that important? If you remember from our previous discussion, an odd root, the domain is all real numbers. We have no restrictions on odd roots, only on even roots. So here we go. X minus 3 is greater than or equal to 0. I want to isolate the x, so I'll add 3 to both sides. X is greater than or equal to 3. So that would be our domain for this f of x function. We're being asked to use interval notation. So as a reminder, I can draw a number line. 3 here. I'm going greater than or equal to 3. All the way up to positive infinity. So my interval notation is 3 to infinity. Try to find the domain for g of x and h of x on your own. If you'd like, you can pause the video right now and come back to it. That would be best. Remember, our goal is that we learn. We're going to try something and learn from it. If we got it right, great. Keep reinforcing it. If we didn't, correct our mistake. So hit pause now, try to find the domains for 12 and 13, and then you can hit replay and I'll walk you through it. For g of x, 3x plus 15 greater than or equal to 0. I need to isolate the x term, so I get rid of the 15. 3x is greater than or equal to negative 15. I need to divide by 3. X is greater than or equal to negative 5, or negative 5 to infinity. And for h, 6 minus 2x greater than or equal to 0. You can do several different things here. I'm going to subtract 6 so that I can try to remind you of a very special, important property of inequalities. Negative 2x greater than or equal to negative 6. When I divide or multiply by a negative number, that inequality symbol flips around. So x is less than or equal to 3, or negative infinity to 3. If 1 is less than 2, if I put negatives on them and I look at negative 1, negative 2, which one is bigger? Which one is farther to the right on the number line? We say which one is bigger because we're wanting what's farther to the right on the number line. Another way to think about it is we want the alligator to eat the bigger number. Or Pac-Man, or whatever creature you want to use in there. Or we want the symbol to point to the smaller number. I've seen that before. Whatever helps you remember what that inequality means. Well, here, -1 is bigger than -2. -1, -2, -1's the bigger one. So that inequality, to make it true, would be in the opposite direction. When we multiply or divide by a negative number on an inequality, we have to change the direction of the inequality to maintain what's true about the situation. We'll talk more about this later on this semester when we get into inequalities a little bit more. So now that we have our domains, we'll give them a yellow highlight here so they're a little bit easier to see. We have 3 to infinity, -5 to infinity, and -infinity to 3. So looking at these graphs and trying to decide which graph corresponds to which function, well, I've got 2 graphs going in the same direction and 1 going opposite. Noticing the patterns with the 3 domains, the first 2 go to infinity, the third one goes to -infinity. This graph is going to -infinity. 13 must match with the first graph. Looking at 3 and -5, these are the starting places for these radical function graphs. So looking at the second graph, it starts at 3. Looking at the third graph, it starts at -5. Going off to infinity in both cases. And so that helps me determine that g goes with the third function and f goes with the second function. Or if we write it differently, the first one's h, the second one's f, and the third one is g. So what's the domain of f of x equals the cube root of x minus 5? What do we need to do here? Do we need to say x minus 5 greater than or equal to 0? No. We have an odd index. An odd index means our domain is all real numbers. In the next question, what do you think the graph of y equals square root x plus 5 would look like? Well, the square root of x plus 5 should be the square root of x function, but shifted up 5 spaces. I'll do a better drawing in a moment. What about y equals the cube root of x plus 5? We would take the cube root function and shift it up 5 places. Draw a sketch. So y equals square root x plus 5. Why do I know it's moved up in this case? Because that plus 5 is on the outside of the radical. And so 1, 2, 3, 4, 5 is my starting place. And if I say if x is 1, 1 plus 5 is 6. 2, 3, 4. If x is 4, square root of 4 is 2. 2 plus 5 is 7. And I get that square root pattern just shifted up 5 places. For y equals the cube root of x plus 5. 1, 2, 3, 4, 5, 6, 7. We can look at this in a similar way. I know if I plug in 0, cube root of 0 is 0, plus 5 would be 5. Plug in 1, cube root of 1 is 1, plus 5 is 6. Cube root of -1 is -1, plus 5 is 4. And we get this little snake going through here. Like so. What happens if the 5 is underneath the radical? This is a left shift by 5, and so is that one. Both of them are left shifts because they are under the radical. Just like in number 15, the plus 5s were vertical shifts. The 5 was outside. So we can draw a sketch to support our answer. Y equals square root x plus 5. 5, 2, 3, 4, 5. And I'll have a dot there. If I plug in negative 4 plus 5 is 1. Square root of 1 is 1. If I plug in negative 1 plus 5 is 4. Square root of 4 is 2. And I get that square root graph. Just shifted left 5 spots. Looking at y equals cube root x plus 5, we get the great curvy shape of a cube root. Just shifted to the left by 5. Let's talk through some more transformations. What would happen to the graph of f of x equals the square root of x if we had a plus 2 on the end? Here would be a good point to pause that video, see if you can figure them out on your own, and then come back. Plus 2 on the outside is a vertical translation. And that vertical translation is up by 2. Here for f of x equals square root x minus 5. Minus 5 is on the outside, so it's another vertical translation. But because we're subtracting 5 from the y value, we have a down vertical translation. Inside the radical x minus 3, that minus 3 is a right translation or a horizontal translation by 3. And then the last one, x plus 4. Plus 4 is inside, so this is a horizontal translation. And this time we're going left because of that plus that's in there. X plus 4, we're going left. Here's another opportunity for you to try finding that domain on your own. So hit pause and work it out. Underneath the radical, x minus 2. X is greater than or equal to 2. We're going to write it in domain. We're going to write it in interval notation. 2 to infinity. Again, checking the index. It's even. Same over here, even. Set the thing in the radical, greater than or equal to 0, solve. In g of x, check the index. Oh, index is odd. My domain is all real numbers. I don't have to do anything as long as I recognize that that domain is odd. And the last one, 6. 6 is even. Since 6 is even, 9 minus x greater than or equal to 0. We can either subtract 9 or add x. I'm going to add x this time since I subtracted in the previous one. 9 greater than or equal to x. Oh, there we go. 9 is greater, so we're going to put 9 there. Negative infinity. Oh, I forgot my domain for this one. Negative 3 halves to infinity because we're still on greater. And there you have domains for radical functions. Radical relationships have real-world applications. We have a formula that models the distance in miles that you can see to the horizon if we're standing at a height of h feet. The height of the Sears Tower in Chicago is 1,450 feet. How far to the horizon can visitors see from the top of the building? Use your calculator round to the nearest mile. So the idea here is we're on top of the Sears Tower. It's their radio antenna. And we can see out to the horizon. So if we have a function, we know from the problem that the height of Sears Tower in Chicago is 1,450 feet. And that's the only thing we need to know in this formula. 1450 divided by 2. Square root 2,175. We end up with 46.63689522654. That's just to round to the nearest mile. 46.6 is 47. 47 miles we can see from the top of the Sears Tower in Chicago. I'll leave the example on autism from the Blitzer book for you to do. You can go into the OneNote and check your answer, and I'll see you next time.